Hello. Hello. Hello.
Yes,
Hello. Hello.
yes, sir. You can speak now.
Your sound is not clear to me. Hello.
Yes, sir. You can speak now. Is there any problem?
I think our speaker has joined. We can start.
Okay.
Okay. So good evening, everyone. A very warm welcome to all our esteemed participants who have joined us on the second day of the Atal AICTE sponsored 6-day faculty development program on seismic vulnerability assessment, organized by the Department of Civil Engineering, Royal School of Engineering and Technology, the Assam Royal Global University. We are delighted to continue with this academic journey with you all with two highly accomplished speakers who bring with them immense expertise and experience. So, our first speaker today for the evening is Dr. Aparup Biswal, an accomplished structural engineer currently serving as AGM and engineering lead at the Precast Works Competency Center, PWCC, L&T Construction. So, please give me a moment to introduce you. With a PhD and MS by research from IIT Madras, Dr. Biswal's core expertise lies in the design and detailing of precast concrete structures, bridge super and substructures. His professional portfolio includes design support for large-scale precast systems, mold planning, and performing micro and macro level finite element analysis. He has contributed significantly to the development of national guidelines for precast practices and actively leads research and forensic investigations on structural performance and strengthening requirements. Over the years, Dr. Biswal has played pivotal roles in landmark projects such as the CIDCO, mass housing projects, Narendra Modi Stadium, high-speed rail corridors, indoor metro, and tunnel lining analysis. He also has enriched academics as a teaching assistant at IIT Madras and as ad hoc faculty at NIT Goa, while guiding numerous MTech theses. Recipient of Ultratech Cement Award for Research Excellence, he has widely published and presented at international platforms. His outreach efforts through webinars, workshops, and training programs highlight his commitment to advancing precast technology and structural engineering capacity building. We are truly honored to have him with us today. Sir, you can unmute yourself now, and we now invite you here to deliver your session.
Good evening, all. Give me a second. Let me share the screen. I hope you are able to see my screen.
Yes, sir, it is visible.
Yeah.
Can we have a photo? Before?
Yeah. Yes, please.
Yes, sir. So, Christy?
I request all the participants to kindly turn on your camera because as for the attendance record, we would like to click a picture before we start off with the session with the speaker.
Screenshot has been taken.
Okay, thank you. Thank you, Jay. Sir, you may continue. Thank you so much.
Yeah. Good evening, all. I thank the organizers and Royal School of Engineering and Technology for inviting me for this talk. As you all are aware about the topic which we are discussing, currently I will discuss something related to monitoring, repair, and some bit of finite element parts where we see how do we calculate the deficiencies. Few part on strengthening. I'll not go deep into those. Even I will not go deep into how structural monitoring is done. Rather, I will explain you the concepts and few examples where I will explain you how that has been done and how you can interpret the results based on those. This is the overview. I'll be having a few slides on Larsen & Toubro. I know you all are aware about the company. We will see some slide breakers having certain photos of our projects. This is the overview of my presentation. We will discuss on common issues, what we face in structures, then what type of techniques we use to detect what is happening to the structure. Can we judge the structure? Can we diagnose the structure based on some parameters? Then once you diagnose, how do you identify the deficiencies? Then what procedure you take for repair or retrofit, or any methodology or any procedure you write down or you follow throughout your projects. Then we'll close this presentation. These are some projects. I no need to explain them deep. You all will be knowing this has been happening. MHSR is our high-speed rail, where you have single segments. That means this is a full scale, full length box cutter. We have track slabs running from Delhi to Meerut trains. We work on tunnels, and currently we are doing precast water tank stagings. Narendra Modi Stadium, again, you all are aware, and Dwarka Express, where we are using box girders, eye girders, those things to build it. Here I have shown you what we do in precast. Again, what we achieved the span, which is 33.3 U girder, which is now going to be the largest or longest span available in India for a U girder. Everyone might be knowing U girder. U girders are used in metro projects where instead of having any box, you have a U shape to run the metro on it. These are some mass housing projects we did. We did 96 days, 96 flats. This is in Mumbai. Now, few months back, we did Mission 45, where we got 6-story car parking done in 45 days. Again, this starts only from the superstructure part. I am not talking about anything on foundation or any short, which is not to be considered in precast. These are some initiatives we are taking. We are building factories now. We are targeting all over India factories where we can deliver projects based on the project requirements. Let's come down to today's topic. This is Mumbai. I know you all will be aware that we are growing. We are growing in both the verticals. Somewhere we are growing horizontally, cutting down trees and occupying the areas. Somewhere we are growing vertically. Are we growing faster enough to get accommodation for all our beings? I don't think so. We are having so much shortage. But remember, to achieve all these, we should not compromise. We should not compromise on quality. We should not compromise on safety. And finally, strengthening should not be need in the day one. In the day one, we should not be targeting that we are going to do some strengthening. And that's what is happening in many projects. Many projects from the day one going to strengthening. And if you go to news and start reading papers, you will find many comments, many lines commenting about these things. Let's see what you expect, and you all will be knowing this book and the page from that book. So we can have defects anyway. That can be non-structural. That means it doesn't hamper my structural safety. It doesn't hamper my strength. Strength and safety is answered, but what is not answered in non-structural cracking is serviceability. Maybe my structure may not perform to the intended function or intended life, or it may do leakage, it may show dampness, it may show corrosion, it may show vibration. Those are due to this non-structural defects. When it is structural, you need to go for strengthening or some sort of enhancing the strength. Both topics will be covered, I think, by multiple presenters or multiple researchers that you will be hearing there. I'll be also touching certain parts out of it. How do you detect it? You can do destructive testings starting from core. Core is obviously a destructive. You take something and break it. You can do non-destructive or partial destructive. Those also we'll touch on slightly. We'll go to the test parts also a little bit. Next, you correct it. Correct. You can repair. That means non-structural goes to repair. Little bit of structural also go to repair. Sometimes strengthening. That means you enhance the performance. You target something more than that. What do we target? We'll see in this slide. So this is where I tell it, or many forensic engineering people tell it as condition assessment. You assess your structure based on the time it has gone through. Everybody will agree that it will decay. And that means my performance is going to day by day reduce. So you may enhance like we are doing nowadays for some structures in the day one itself. You enhance it certain strength, then also it is going to decay. Or sometimes you come and do a retrofit and enhance it to a new life or new design intention which you are intending. Like let's assume currently IS 1893 is getting revised and certain zones will go higher and you may be having higher forces. Now I may strengthen my structure to go for a new strength criteria and new life criteria. And these two parameters you see, vertical axis and the horizontal axis, both can be enhanced. You can target enhancing the time span of your structure without touching the structure condition or strength, or you may enhance the strength. Ultimately, the time span will also get improved. Now, these two, you do condition assessment. And then what causes you are looking at? You may look at design issues, which has come due to the designer's mistake or miscalculation or misprediction of the forces. Manufacturing damages, that means something which has come because of construction issues. Service induced, it generally means you have intended for X amount of load, and now you are doing something higher, you are applying something higher. Let's see some more details. Once you go to do condition assessment, you do initial inspections. You go to the site, you inspect the structure, which for what you are doing condition assessment. And in that process, you may go for a detailed investigation. In that, you will point out what other type of test you are going to do and what type of analysis you are going to do. Then you report it. So main part which we sometimes miss is we don't report many things what we observe. We may think that it is non-structural, we may think that it doesn't hamper the structural safety, but later stage that small part is going to lead, which is the structural failure. Then what symptoms or causes will like once you go to a doctor, once you say that I am going with this disease, he may not treat only the disease, he may ask you lots of questions. So we should be thinking about lots of questions here, and what is making that to happen? Is that because of life which has gone for corrosion, or it is in the initial stages where thermal and shrinkage cracks has come? That is going to come for high strength concretes, and slowly actually we are looking at more higher strength concretes. So we should be looking at how we dissipate or we go out of the shrinkage and thermal cracks. Some areas we may have acid attacks, we may be talking about some chemical plants where we get this type of acid attacks. We may be having aggressive environments because of the water, we may be having some reactions. That generally depends on where we are doing and what we are doing. Now, once you go for inspecting, you do initially visual inspection, and mostly 80% of the defects you will be able to find out. It's not, I told you, like you don't find out and stop there, you report it, you note it. It may be helpful today, or it is going to be helpful tomorrow based on the structural performance. Then what you will be using, so many things are there. You may require multiple of these things to access a structure, and these type of defects you may be able to see. You may be seeing some honeycombing, you may be seeing some cracks, you may be seeing dampness, but those localized reports are actually going to help us while we are doing rigorous structural analysis or trying to find out what has caused these things. These what limitations we have in this visual inspection? Who is going, whether he is qualified to look at it, and what he is looking at. Again, it is maybe reliable, it may not be reliable depending on person who has done the visual inspection. Now, once you do visual inspection, you have concrete members. You may look at cracks, which are these. You may tell fine, okay, I have a fine crack which is 0.8 to 1.5. Someone else may not tell it. You may tell that, okay, I have a medium crack which is between 1.5 to 3. These are some examples I am writing. You may not be able to see certain cracks. Maybe someone else is able to see because he has a better eyesight, but he has gone with better instruments. Similarly, when it comes to steel members, you should be looking at all these, whether bolt has corroded, whether member has corroded, whether member has buckled locally, or member is showing some crimping or buckling locally. So those, again, depending on who is inspecting, what is inspecting. Let's assume we are going for a bridge inspection. We may not be following all these rules at every locations. I know this is a flexure governed location. I may be looking at flexural cracks, and when we go to shear governed locations, we may be looking at shear cracks. Now, these two differences make sense only if you are qualified to know that there is a difference between flexure and shear cracks. If we are not aware what to be looking at, then we do a wrong report or wrong visual inspections. Now, based on the visual inspections, we will choose generally, it is common practice that we come up with a non-destructive testing. What from the non-destructive testing we'll be looking at? We'll be looking at multiple activities depending on what structure we are doing. Let's now go to the detection techniques, which has destructive, non-destructive, and partial destructive. Wherever possible, I will give you an example. I will request if everyone can keep the video off, because I'll be able to see you in the video. So more common practice is core test. We suggest core test depending on what we are intending to look at, and how many cores, normally 3, and what codes to look at, these are the codes to look at. And once you take a core, remember, cores are susceptible to errors. You may have taken a proper core or not proper core, that also matters. Whether you are crossing the reinforcement or you are cutting through a confined area, you may get a higher strength. Maybe that's not the required area. So you should find out which area to be taken for the core and what ultimate strength you are looking at. Are you looking at in the confined areas, or are you looking at in the unconfined or normal reinforced areas? And depending on your test sizes, you may be sometimes getting the aspect ratio proper. That again, we will be going to the code to know whether we got the proper aspect ratio. If we didn't get, we may correct the results based on that. Always remember, codes tests are susceptible to crack at the top and bottom of your loading areas. Those are the platen areas which get stress concentration while loading, or if you have not taken a proper core or not done the proper packing at the top and bottom, you may get a top failure. Here, the minute crack is visible here. That's where the crack is expected to happen, and that's how the failure is expected to happen. Or you should expect a normal cylindrical failure, which a normal cylinder does for a normal core which you have tested. If your failure pattern is random, let's assume I got a shear of here, you should not be taking that as the result for the core test, because that is not the proper failure which we got, or maybe we got a crushing at this localized regions. So those also we should be avoiding at. Now, always we have so many old structures with machinery or bricks, and we want to know the loads. So the test is flat jack. You can go with this type of test with pre-marked distances. That means these two distances are pre-read. Then you cut. Once you cut, because of the pre-load applied in the structure, this area is going to deflect. Then you put these flat jacks and try to bring it back to the original displacement what it was. In that sense, you will be able to know whether your wall or structure is having any vertical load or not. Why do I need it? I need it to access the life of the structure, to know how much load I am expecting, because many of the structure we will not be able to calculate the actual load. And sometimes these masonry structures are not a homogeneous structure. They may be having multiple leaves inside it. That cases also will be needing to know whether those effects are there or not. What can be error here? Multiple errors. Like I told you in core cutting, similarly here, depending on the morphology of the structure, we may have errors. That also we need to take care properly. This is the standard case which we are expecting. We may get multiple different cases. Now, how that is been done? Let's take some local peer at some location. So initially it is marked, initial readings are measured. This is a DMEC, it is a mechanical gauge. Initial readings are measured, then you mark where your flat jack is going to come. You fix the device which holds the cutting wheel, then you cut it. Then again you start doing the measurements. In that sense, you will be able to know how much load you had it here, and with those limitations which I pointed out. Similarly, I can have pull-out test. Let's understand these concept. Here you have this bully, you are pulling it out with certain reactions, and you are expecting certain failure modes. Depending on those failure modes, we can calculate the stresses we are expecting. You have multiple names depending on where it is originated and how the device looks and what diameter it is and how the force application methodology is there. Sometimes we install it prior to know the strengths. Sometimes we do it on the surface. This is known as pull off. Again, we are expecting here to, from the pull off strength, we will be able to predict the compressive strength. These pull out or pull off depends on how many repetitions you have, how you have calibrated your graph. That means you should have calibrated your graph much well before to know that if I have a pull off strength of 1 MPa, I'm talking about a 15 MPa concrete. If I have a pull off strength of 4 MPa, I'm talking about 50 MPa concrete. So these things are there. Next is rebound hammer. I'll not touch at all. This has limitations. This has multiple methods to read it, and sometimes it only talks about surface-based concrete's quality. If you have done proper packing at the surface base, you may get higher strength. Then that doesn't convey that your structure has the highest strength, whatever you have reported from this test. Let's come to now widely used, I can say that misused test, which is UPV. There are three methods, direct, semi-direct, and indirect. All three methods are being used and you get some output. Remember, these curves make sense sometimes, and sometimes you need to understand this is where your reading lies. You may skip the first point, or you may go to a next point wherever you want, depending on what you are looking at. And I will always suggest, whenever you get a machine like this, which can give you this type of plot, you should see what you are getting. It's just not machine showing some reading. Let's assume this is the curve, and sometimes I am getting just a flat line, and machine is showing some time. You just reported that without knowing what has happened inside the structure, whether the receiver has received something. So transmitter transmits something and receiver receives something. Receiver might have not received anything, and you got a time from the machine and just reported it as the time, and based on that you reported the quality. It depends again what thickness you are looking at, what material you are looking at, whether the material has any defects or not. We'll see some examples in this also. This is where indirect method comes. We have used it to know the property below materials, like whether layers are there, whether poor and good quality layers are there. You will get velocity transmission curves having different slopes. So if I do plot time versus distances, I get different slopes. It means I'm entering to a different phase of material. At this point itself, I am entering. So I can know what distance it has taken to enter to different materials. From that, I can calculate what is the first layer thickness and what is the second layer thickness. And here you are seeing multiple cases. In this case, there is no transmission of wave, but dip this in water or go to a area where moisture is high. You will see that this will start showing values. Please remember that's a wrong value. You should have not done that test in a highly moisture test or conditions where path is there to pass through the web to the next. You will report some higher values. You may report that quality is bad, but this is the true condition which is supposed to happen. Again, reinforcements will affect the results a lot, and we can use UPV to get the crack depths. I will show you in the next slide how that has been done. This is some peer where UPV is done, and this is the table we generally use from our code to point out what type of quality and all we are talking about. Let's talk about the experimental case. Intentionally, some things has been done to understand what happens between surfaces, and there is a grout poured in this joint, which you can see in this here. And you can see beyond the grout, the lines which were almost straight started opening up or started flattering or changing the slopes. That means something is happening at the joints and some slope changes are occurring there. Same method we can use to get the crack depth. We assume certain assumptions like this is the path which web takes to pass and this is the distance. Based on that you calculate. Same thing if you do, you will be able to know what crack depth we are looking at here. Now, is it reliable? It is reliable depending on who is taking the measurements. It is not reliable depending on what condition he is taking the measurements. As I pointed out, it depends on how much steel is there. It depends on whether you have moisture in the concrete or whether it is raining, whether it is a very dry day. So all these factors will matter, and you can have a calibration error of 20%. That means in your machine itself, you will be having those factors affecting it. Next is tomography. I'll tell this test is more sophisticated than UPV. It uses the technique of ultrasonic pulse velocity, but it goes much beyond. It's like our CT scan machine doing CT scan of our brain or any body part, and it starts detecting dense material, loose material, or locally loose material in a similar concept what I spoke in UPV. And there are multiple machines. I may not require to name it, but there are machines which can do tomography study. Let's again go back to the specimen which we are talking and see how tomographic study is done. And we will go to a live project also where it is done and what has been found out from there. So if you see this tomography here, we have intentionally pointed out how many probe points are required or how many transmission and receiver points are required and how those distances will be. Too close between the probes are also dangerous. Too far between the probes are also dangerous. And what is the intended paths which we have in this flow? Then what is the periphery of that we are looking at? So we can go to various tomographic available softwares and start doing data input, then do preliminary, like what type of paths we are looking at. Then we defined what area we want to concentrate at. Then meshing is the parameter where you know that this is the probe distance you have taken. So if I say these are the 2 points which I have taken, based on that how finer I want to go in the tomographic curves. What tomography will do is whatever data we gave him, it will start calculating the error. Error means it knows from here to here the path is having a x distance and the time taken by the machine is t1. From here to here, the path becomes x plus delta. Time taken should have been t1 plus delta 1. Now let's assume that time taken is something else other than that. So it starts calculating what could have been the alternate path in it, which it took to reach that point. And it has multiple options to take. Based on that, it will start telling you the intended error function you had. Beyond that, how many points are there, and below that, how many points are there. And it starts giving you a plot which is velocity contour plots having different colors depending on your intention. So my intention here was to give 4000 being the good quality concrete where concrete has no defects, and 2000 being the least poor quality concrete where concrete has some impurities or defects or interfaces or something. So what I can show you that something is happening in this zone, and in these dark zones, it is a good quality concrete. So that we understood in the initial itself by UPV, where I showed you the curve changing the slope between the segments. Similarly, you can see here where I have taken two different cases, one with defects, one without defects. You can see tomography is easily answering that. These are the zones where defects are concentrated and it requires certain concentration or certain strengthening or certain intervention or grout injection, and that can be taken care locally in these regions. When it comes to this case, we are almost having a uniform concrete. I should point out here and here I have the joints which supposed to have some defects, but that has been taken care in the hacking, that means roughening of the joint and grouting while filling those joints. Let's take some real application. This is a dam. What we are looking at is seepage points. There are machines which has been used to do that, and multiple receiver and transmitter points, and this is what the output looks. Again, the highest value of 5,000 to the lowest value of 2,500, and marking of patches where higher values are there and lower values are there, where little bit of intervention may be required by means of injection of grout based on various methods. So we don't stop here. From here, the strengthening people will take over. They will start analyzing your results or your findings and start devising the method how that can be strengthened, or grout can be injected, or seepage can be stopped. Again, is it a best method which gives us everything? My answer is no. None of the techniques can be best. You need multiple techniques to answer the same question. You may be looking at multiple times to find out what is going on in the methodology. So what can go wrong? We have properties which are multifold. We have properties which are nonlinear. We are talking about materials which are nonlinear. So first method thing is going to affect us is nonlinearity in our materials or members or interfaces. And how the wave we are transferring. Are we able to produce that much of impact or that much of vibration which pass through this and goes to the receiver point, or are we not able to produce? That also matter. And again, who is doing it? Is he qualified to do that? You cannot give a machine, whether it is stethoscope or whether it is anything, to a layman and tell you please read it and give me a meaningful result which I'm going to use. So we should be cautious, like the company we have appointed, the people we have appointed is able to do that or not. Please keep your mic mute. So with that background of destructive, I don't know whether questions in between is allowed or not. Yeah, please keep the mic mute. We will take all the questions or doubts which are raised towards the end. I think that's the methodology here. It is getting adopted. I am not sure. Shweta madam, you can clarify if in between questions are allowed.
Sir, we would request you to please complete in one go, and we will take up the question answer session after your presentation will end.
Yeah.
Thank you so much.
So thank you all. Please be patient. I'll be available for all your queries and questions, whatever rages. Let's now go.
Humble request to all the participants, please raise your queries in a question answer session. Thank you so much for your cooperation.
Thank you. So we covered starting from whatever issues we are looking at, how do we condition a structure, what type of detection techniques we are looking at. Let's now go to how to identify the deficiency or quantify the deficiency. So what we will do is, first is detect. What you are going to detect is visual inspection, we already covered, and built versus design drawing. So you should understand what intention the engineer had and whether he has achieved it, whether the intention of the designer or the function of the structure has been achieved. That means that also need to be compared. Then you go to diagnose. In this, you put or adopt a method from NDT-DT. Then geometry verifications. Here I'm talking about the sizes. You may be thinking that everything will go good, but the guy who is reading, he may have read it 300 as 200 and 600 as 300. Then he will end up with a different size. Whether that has been verified at site level, I doubt, because so many structures are going on. We have limited engineers at site to verify, and sometimes we depend on the contractor directly or unqualified contractor directly without thinking much. Then analysis. Preliminary is always like what you did design with softwares and trying out to understand whether the design and the intended function of the structures are getting satisfied or something else is there. Then you take a decision. In this decision, you may think about, I will go for micro or macro level finite element softwares and go deep into the analysis. I may compare the design intent and I may go with deficiency calculation. Always remember, after diagnosis, that means initially that preliminary report, if it says that everything is answered, let's assume I know the beam should be simply supported, and in design intent it was continuous. In site we have achieved a simply supported beam, the beam is going to crack. Now I know the answer, so I should be pushing it back to the original position. If it is possible, push it back, strengthen it depending on that requirement, get the continuous arrangement available. But let's assume we are talking about a location where we are not able to understand the force flow atta from the preliminary or 2D or normal 3-dimensional analysis. There we go to the local finite element analysis. Here the cost increases a multifold. If you have given X amount here for this analysis, you may go to 100X, depending, it may go much higher also, depending on what structure you are looking at. In this, the analysis guy will not be looking at just the design intent. He will be looking at multi-dimensional. He will be going deeper into your concepts. He may think that, okay, you intended a corbel and you didn't get that, or you intended a deep beam and you didn't get that. You intended a tall column and you have got something else. Or geometric instabilities, like you supposed to have a straight beam, and during construction it has gone curve. Now here also I should answer it clearly. It is not like if a beam which is supposed to be straight and became curved, that doesn't mean that it is structurally deficient now. It may not be, depending on what steel we have provided, how much extra we have provided. That means that margin we had in the initial design calculation, it can built in and start making my structure safer rather than requiring a strengthening. Now deployment, what to deploy? Are we going for strengthening or just a repair is enough? Do I need temporary measures? This is the important part. Sometimes we know the deficiencies and we start waiting. Let's assume we know the crack is there and it is Goa or it is Mumbai. It is getting interacted with the corrosive environment a lot, and we start waiting for 2-3 years to finalize that, okay, now finite element guy has given me a solution. So better not to go to the decision phase. In the diagnosis phase itself, you tell that I need temporary measures. So I need to cover it, or I need to paint it with on non-corrosive environments, or I need to provide props to my beams. Like I told you, a simply supported beam which I built supposed to be continuous. Now I need to provide props. Otherwise, what happens? It keeps on deflecting. Load is there on the structure, means it will keep on deflecting because crack is keeping on growing slowly. And what timeline you are looking at? Is it today you want the solution, or after 5 years you want the solution? Because we saw in the beginning itself, condition assessment gives us a phase where in between we can enhance the structural performance and get a better performance for the longer life of the structure. Then I pointed out every slide that you need to report. You need to have proper drawings. We are engineers. We will only understand drawings. It may be 2D, it may be 3D, depending on the project requirements. And what did we do to the structure? Did we repair? Yes. Then please note it down. This is what been done to the structure during construction, and this is what been done to the structure after construction. So each stage can be iterative. It is not like I wrote it, so this is the final. I might have not followed all these everywhere. Then these workflow requirements will be dependent, and we may automate or digitize the processes. Let's now go to some finite element example. Here I'm just talking that what finite element can do. You can go to any member. It can be column, beam, or it can be anything depending on your structure. You do a initial model, which we spoke, it will be always a line model. Then from the line model, you understood that you are not able to understand few of the concepts or few of the transfer mechanisms or few of the designer's intention. Designer is strongly telling that it is safe, and the contractor or the client is not having any faith. He is telling that no, it is not safe, it is having these many problems. Now designer wants to prove you, so he will go to the rigorous finite element, where I go to a local element. Now here I showed you the complete span, which is balance cantilever and having everything, having bearings, having the pile cap, piles, piers, every details. But when I came to here, I want to prove only the concept of the box girder, or only the concept of the diaphragm, or only the concept of some part where I want to show. Let's now see one example here where certain cracks has come to a box cutter segments. So what we saw some cracks. We saw some orientations. These need to be reported. Like you saw some marks here. Intentionally, I have blurred it, so please forgive me. Then what else you are able to see based on your observations? Are you seeing cover concrete, or are you able to know the depth? Are you able to know the structural part of those cracks, or reason or root cause of those? If you are able to see. If you are not able to see, just put a question mark and send it to your designer or who is going to analyze it. He has to answer these, how these has come. So let's see what extra data we saw. This is not the real pictures. These are also not the real pictures. You saw that cracks are there in this, and you took cores. So some NDT has been done. That means UPB, rebound hammer has been done. Then core cutting has been done, and crack depths were shown. So now in these observation itself, it says that some cracks are stopping here. So now you need to know whether it is cover. If it is cover, how much cover it is, because sometimes you may end up in higher cover and end up in a crack. Your thermal crack has gone till the cover depth, or shrinkage cracks has gone to certain depths, and find out the pattern of the crack. Based on the pattern of the cracks, it will be showing like how it has been done. Now go to the analysis software, start analyzing and start understanding the results. So here what has been done, some schemes were decided, what can be the cause, what was the root cause, and how the cause being treated, that has been identified. And finally, the roots are shown. Like we saw some lines like this marked earlier. These are the straight cracks which are possible. We saw some lines which are going slightly inclined. These are the patterns which are found out. And we saw some diagonal, pure diagonal cracks. These are the regions which are found out. Remember, all these are bending moment plots found based on the analysis for a particular case, and the roots are found, and based on that, the crack patterns are predicted. In this prediction itself, we'll start predicting what has happened to the rebars, whether the rebar has yielded, whether do I need to replace them, do I need to strengthen them. Let's take one more case. I showed you one case with bridge. Let me show you one case with a building. Here, this part of the beam was resting on this beam with a support, and what you see is failure of this corbel. There are multiple locations which are supposed to fail in the later stage, and we need to find out what can be done. So this is what was intended. This part supposed to come from the primary beam with some doubles, and these green color beam has to rest on it with that double and do the function. What next? Let's find out what can be done. What to be done is you need to strengthen. That is true from the day one. What methodology you will take? Because these are two separate parts, mechanical methodology has been taken, and some plate with some bolting methods has been found out. Here you can see one more sketch showing so much of rigorous part. This is being done because certain locations the loads were quite higher, and only this cleat angle with these bolts were not sufficient. Now the load has to be transferred to the beam top by a mechanical arrangement, where this hanging arrangement was built and the load is now getting transferred from this part of the beam to the green part, which is the monolithic part. Now, once you do that, you will ask, like, what will happen to the corrosion? What will happen to the service life? Will the steel part will be visible always? Now we need to hide it. So you see some casing, and then we start putting it with the grout. When it comes to analysis, individual parts are analyzed for different forces. And in this part, intentionally, all loads are analyzed for one part itself, so that the bolts are always in safe. If and all because of some uncertainty, one part is not erected properly or not fixed and the load is live on the structure, then one single parts has been taken. Then failure modes for the bolts, failure modes for the plate, failure modes for the sections is taken, and the final strengthening scheme is proposed. Let's now go to some repair methodologies. In that also, I have one more strengthening scheme. This is how we at our company report the works. Whatever observations are there, we will make a formal report and get it approved in the beginning from the client that this will be our methodology for repair, this will be our methodology for rehabilitation, this will be our methodology for injection of grout, and these are the cracks which will inject or something which we are going to do. So in our projects, multiple cracks can be possible because environment is not in our control. Today it is raining, tomorrow it will be very dry day. So concrete is susceptible to all these parts. So these can lead to multiple types of cracks and multiple types of deviation from the intended functions. Let's take some precast example where I had a wall with projected dowels, and this is what is intended. Your top wall will come or pass through all these dowels and match properly. It's not true always. Sometimes what happens, this we wrongly placed at here. So the yellow dotted line you are seeing, now you can see the black line I'm highlighting. I have placed it here. Now this dowel will never match here, or I cannot bend it and take it. So what to be do, or what can be done? Sometimes what happens, this red dot is not at all there. We misplaced it. We don't know. We forget it. Or somehow we have cut it. At that time, what to be done? So what factors will affect us? It will diameter of the bar. Are we talking about smaller dia bars, larger dia bars? What is the position? How far it has gone? What orientation it's supposed to be? And what strength of the concrete we are talking about. It's not like anywhere we can drill or anywhere we can fix. So based on that, we come up with certain methodology, like we need to drill, we need to insert a new bar, if dowel is required and installation is required for a new dowel. For the dowel which are locally adjustable, like the one we talked, which is just next to the dowel tube. So what can be done? You locally chip out the concrete, bend based on the design requirements, which is 1 in 6. Everybody will be knowing, whoever is in site, to do that. So based on that, you change the orientation and get your intended function. So that only can be done if you have sufficient depth available to break out or sufficient width available to break out, and you are locally able to adjust it. Otherwise, you go with a new installation method. Then you start reporting it. That's what being followed. Intentionally blackened out or covered details which are not required to be shown to you. So what we have followed is detect. So you find out what is going on. Diagnose. You find out the cause, what has been required, and where it is now. Take a decision whether it is new hilty or old being bent. Then deploy your method, do that. Finally, you document it. These 5D techniques need to be followed, and you do it so that you have a proper report for your future and for your next project. Before taking the project itself, you can tell, these are going to be my methodology where I do these works in this way. Now let's take one more case where I have a beam coming from two walls with a cast in situ slab. So this color is CIS slab. I have two orthogonal walls and the beam is there. Now top bar of the beam goes into the CIS slab and bottom bar of the beam supposed to go into these walls. And we have completely forgotten to remove the rebars from the walls, and the beam is now being ready to cast. Now in this case, so designer would have told you, okay, for this beam, I need 3 bars here. Now, if you see, this is only some 150 or 200 mm. A bar in the beam can never be developed here. And if you go to any mechanical anchor people, they will tell, I cannot develop also. And you can never drill perpendicular like this and bend a bar. That also cannot be inserted. When it comes to top, you have freedom. You can just put a rebar at the top in the CIS concrete and do that. So here what matters now? Diameter of the rebar, what we are looking at, position of the rebar, where it was, orientation. Like if you see in a thin wall, it's supposed to come like this. And strength of the concrete, thickness, do I have sufficient thickness to drill in? And again, orientation of the panel also mattered. In this panel, you may have sufficient depth to drill in and put a bar, but in this panel, you didn't have. So these are the certain requirements. Now let's see what has been done. The designer requirement was 3 rebars. Intentionally, one extra rebar is added. You all will be aware that if development length is not available properly, we can increase the steel based on the development length required. So based on the same scheme, increase in steel is proposed in the part where lesser drilling depths are available, where larger drilling depths are available, actual rebar are kept, and at the top, because it is a CIS concrete, that also is taken care. But if it is not CIS, locally, if it is a already cast member or already available member, we could have drilled into the slab to lock it, or we could have taken any mechanical method to lock it. Remember, all these scheme also can be tried out with steel, like I showed you in the previous sketches for the corbel. Again, same methodology, you detect it, you diagnose what were the requirements, what designer intended and what you achieved. You take the decision what to be done, you deploy it, and you document it following the same 5D methodologies. As I told in the beginning that I belong to precast initiatives, we have a lot of precast planks. When I say planks, they are thinner sections, but two-dimensional, that means length and width are higher. Once you cast it flat, you are suspect to get lot of shrinkage cracks. Those are non-structural in nature. They may not hamper your structures, but we need to close them. So now we will see some grouting methodology or injection methodology for those. So now what will matter? Slab design consideration and how the slab is designed, whether this is just a sacrificial one or whether it is part of the main CIS concrete. Normally it will be part of the main CIS concrete. What thickness we are looking at, what topping thicknesses we are looking at, that means CIS concrete we are looking at, and what type of waterproofing is done on the top, because all those cracks can be through and through, and if you have not sealed it properly and if you have not protected properly, you may get water leakage. So let's see certain patterns of the cracks based on these and certain holes you are seeing. So those are the holes where we intended to fill it through the injection grouting, and we intended to do a top epoxy nozzle grouting. It may be injection, it may be gravity, depending on what height it can flow through or what depth it can flow through. It may be bottom, it may have not penetrated full depth, only locally it is there. Same, you mark the grid, then you mark the holes wherever it is going to be done, then you inject it from the bottom, but you need to seal it properly. It's not just the epoxy injection because it starts leaking. So you need a sealing properly. Same 5D methodology we will take. We will detect, take the diagnosis, think what designer intended, whether it is non-structural, structural, whether can be closed, whether waterproofing is there. Then take your deployment and document it so that in the later stage in your future projects, it helps you, or in the current projects, whenever some inquiry or some investigation occurs, you are able to support that with the data. Let's take one more case where structural strengthening is done. This is a tank These are some precast walls with bottom being a slab. This is the CIS pour being done with some shuttering so that this tank is tight, watertight, because precast has so many joints. While doing that work, what happened? This wall, that means this wall, these and these orthogonal walls started displacing. It is mainly because they were locked at the bottom and the grouting or the locking was not proper. Now the first thing is, can we reject it? Do we reject it? Do we just recast it? Or we start finding out what can be done? So that two things, like in the decision you are taking to understand what type of diagnosis can be done. So in the decision you took that, okay, this is panels are not cracked fully, only from this dowel it has bent. So panel can be refurbished or can be reused. So now you go to the deeper analysis to understand what has happened. So from the analysis, it can be seen that this much of load, which is making a horizontal thrust here to the wall is not able to resist here as a bending. It's a pure cantilever. And same is not observed for the other two, because these two might have a proper grouting at the bottom or proper filling of the grouts at the bottom, proper connection. And in structures, generally, once one part starts failing, that part has changed the structural deficiencies or force transfer mechanism. So what is being done? First, you brace it. Initially, this is being braced before taking all those call that this has to be reused, this has to be re-strengthened or something. Then you remove this much of the concrete which were disturbing or which were causing the problems. Then you push it back, same mechanism, push-pull mechanism. You rotate it, push it back to the original intention. Now this is straight. Can I stop it here? No, I need to do something else. So we calculated how much force is coming here. Luckily, we had top concrete where we are able to anchor it. We re-established this connection and bent it properly so that it is been answered. And we inserted these with the walls and locked it to the top concrete so that all those forces, whatever were coming as a cantilever, now doesn't come as a cantilever, it comes as a propped cantilever. So now there is a prop here, there is a support here. It may not be fixed now because there is certain rotations happening. Same methods, we took the detection, we diagnosed it, then we took the decision based on the diagnosis, then we deployed the methodology, and finally documentation is done. Slowly we are moving towards summary of this presentation. Again, I told you some slide breakers with Statue of Unity, which is being built by us. So what we saw is 5D techniques, which is applicable to all concepts, starting from the finite element parts, non-destructive, destructive. I don't think that I have gone deeper into those methods. There are various other methods. You have infrared, you have ground penetrating radars. You may be having some other methods where like impact echo. So different methods with different requirements are there. I have not gone deeper into them. I have only touched which were being used and which are being maximized so that you get some functions out of it. Then the structural strengthening requirements, in that I have pointed out how the deficiencies are calculated based on rigorous finite element and basic normal say 2D or 3D when ETAB or STAT. Then going back down to the softwares which can do rigorous finite element like Abacus or ANSYS. Then based on the finite element, identifying what to be done. With two examples I have showed, multiples are there, but I may infringe into confidentiality. I hope you don't use those photos and slides just like that to show someone. So I end here. Let's open it for the questions. Thank you all for listening and not disturbing in between.
Thank you, sir. We now open the floor for questions and answers. Questions from the participants. So may I request the participants to unmute themselves and ask the questions? Or if not, then you can also post it on your chat box.
Please feel free. If I don't know, I will tell the answer is I don't know. But if I know, I will answer it. I will give you the answer which I have.
Requesting the participants to
Hello, sir.
kindly.
Yeah,
Sir.
hello. Yeah, please tell me.
Sir, you have shown some slide. You have shown one precast building, that construction of precast building.
Yeah, I'm not able to hear you clearly.
So can you hear me?
Yeah, I can hear you.
Sir, you have shown one precast building construction
Yes. Mhm.
that has been done within 45 days or within a period of. So I
Yes.
want to know what method that have been used, like doing that.
See, when you say something is done in a lower period, you need
Sir.
proper planning at the beginning. See,
Okay.
planning phase starts from before that 45 days. It doesn't include the design phase or it doesn't include the planning phase. So we plan it. Now in somewhere else in a factory, the elements are ready. See, it is site activity which is making the sense getting reduced. But somewhere else in the factory environment, where in a covered environment, we have produced the elements. Almost in the day one, we have produced something which can be giving me almost 1.5 stories. So that many elements being prepared and properly planned. So let's say that I am telling that I need this structure in 45 days or in 10 days. So you need to calculate how many elements. Let's take a building having 1,000 elements and I want to do it in 10 days. So per day about 100 elements I have to erect. Maybe my crane working hours is 4 hours and it only can erect 25 elements. So I need 4 cranes to erect those 100 elements. Those planning and where it is placed, how well it is placed. If let's assume crane takes lot of time to take from one position and to put at other position, then that hauling arrangement is going to drag out or eat out your time. So that also we need to take care. And design phase where you aim that type of structure where your connections are aimed properly, you plan everything, your members are planned such that it fits into the required geometry, and your molds are taken care for the repetitions you are intending for. Yeah.
So like it is all pre-planned before the
Yes.
setup.
Yes.
So
Correct.
like all the targeted strength also we will be calculating before.
We have achieved it. Let's assume
Okay.
you need 28 days strength to be achieved. We might have achieved it in 7 days.
Okay.
Yeah.
Thank you, sir.
Yeah.
So we have a few more questions in the chat
Please.
box,
Yes.
and I'm narrating those.
Yes.
One from Jagdish Bhumishetty. Any standard code of practice available for tomography and flat jack methods?
There are HTM methods. You just need to see them. I don't remember the code numbers, but HTM method is there for flat jack. Tomography, based on tomography uses ultrasonic pulse velocity method. So you can use those. I think 1199 or something that code is.
So another question from him regarding the strengthening of CIS slab. If it was done using steel, what could be the solution?
See, there are multiple. When you say I'm planning to strengthen something using steel members will be connected using bolting or welding. So if I provide any member at the bottom, it is a beam now. It goes to the supporting structure, which is my column. So you need to find out whatever load coming to the steel beam is getting transferred to the column properly. If you are not able to achieve that, don't jump to steel just like that, because column might have failed at localized area because of that concentration of stresses. So if you are able to connect to the column properly or to the supporting member, whatever it is, it may be a beam, it may be a wall. If you are able to transfer that localized forces, then you plan for the steel beam. Or sometimes what you can do, you can enhance the strength at the column location itself by jacketing it or enhancing it or transferring it from the column to the nearest below supports by a steel member method itself. then we can plan. So when it comes to slab, you will always think about longitudinal or transverse beams to take care of those loads. I will always prefer bolted connections so that at site I have that tolerance to play. Welded, if I am able to do at site properly, that can be achieved, but tolerance to play may not come. Let's assume after connection, you want to move it slightly. Bolt has that tolerance to give you.
So another question
Yes, please.
from Pratima. She's asking, so which is most reliable method of structural audit and compulsory to perform?
Visual inspection by a qualified engineer, I will say, he who knows the intended function of that structure.
Right. Thank you, sir. I think there is another Arsalan Khan.
Yeah.
Yeah.
Yeah, Arslan, please.
Thank you.
Yeah.
Thank you for your presentation. Very nice presentation.
Welcome.
And actually, I've been working in similar fields, but more focused on FRP strength.
Mhm. Yeah.
I was wondering if, like, if you are in LNT, what's the name of
LNT, Larsen and Toubro.
LNT? Yes,
LNT, yes.
working in India, right?
Mhm.
So, what sorts of codes for retrofitting you follow? That's my first question.
We follow for FRP, we follow the same code which you are talking about, ACI 440.
Okay, ACI 440, yes, that had a
Yes.
provision. That's correct. Yes, yes.
Yes.
That's good. Another
We
code.
have one more code for structural monitoring, but ACI 440's calculation methods are much wide accepted because it
Yes.
covers many failure modes,
Yes,
starting
yes,
from
that's
debonding to your FRP failure itself.
exactly. Yes, I think you have already answered my second question. Thank you.
Okay. Yeah.
All right. Thank you so much. So with this, we come to the end of your session, and thank you very, very much, for such an insightful session. We will now, as the questions have been answered, we'll then move on with the second technical session, sir.
Thank you.
Thank you.
So
Thank you for.
Can I leave the meeting?
Sure, sir. Thank you so
Okay.
much.
Thank you.
Our organizers will get in touch with you.
Yeah. Thank you very much.
Thank you. So with this, we move on to a second session of the day without much ado. Yeah. So as the second speaker has joined, Madam, please let me introduce you to our participants here. So yeah, it gives us immense pleasure to introduce Professor Nayanmani Chetia, Professor of Civil Engineering at Jorhat Engineering College, Assam. Dr. Chetia is an alumna of Dibrugarh University, where she stood second in civil engineering and went on to complete her MTech in structural analysis from IIT Guwahati and her PhD from Guwahati University. With more than 25 years of teaching and research experience, she has made significant contributions in the field of earthquake-resistant building design, geotechnical foundations, high-performance concrete, and bamboo-reinforced concrete. She is the recipient of the AICTE Career Award for Young Teacher 2008 and has guided numerous postgraduate and doctoral students. Her research has been widely published in reputed national and international platforms, including conferences in South Africa and Turkey. Beyond academics, Dr. Chetia has served as a Board of Studies member, PhD supervisor, and secretary of the Women's Cell at JEC. She is also a regular resource person in workshops and seminars on disaster management, road safety, and earthquake-resistant design practices. Professor Chetia is deeply respected for her scholarship, mentorship, and service to the engineering community. We are truly privileged to have you with us, madam. Ma'am, I invite you here to take the session forward.
Thank you. Good evening, everyone. Good evening,
ma'am.
Dr. Good evening, Satambara ma'am, the coordinator, and Rishikesh Dwara, the co-coordinator of the AICT FDP program. All the organizers and their participants, I am very happy to be here to share our work on bamboo structures. Now, as already explained, I am Nayanmani Chetia, and today actually this is a discussion. Time to time we have done some projects, master's projects on bamboo structures as well as the bamboo reinforced concretes. So we are going to present some part of that. Okay. Thank you.
I think madam is having some issue in connecting, sharing the screen. I request the participants to be there. And
Yes, I am trying to share.
yes, ma'am. Getting it. I think, yeah, it will work now.
Is it working now?
Yes, it's working.
Okay.
It's working.
Okay, let us start.
Yeah, but ma'am, your video is off. If at all that is fine, then it's okay for us too.
Oh, it's fine.
Okay,
It's
okay,
fine.
okay.
Otherwise, it may create some problem. Okay.
Yeah, okay.
If I am audible, then it's fine. Okay.
You're audible, and your PPT is also visible.
Yeah. Okay.
Okay.
So today's topic is my assigned topic is sustainable reinforced construction using bamboo. Now, talking about the construction using bamboo, actually we have two types of bamboo construction. The first one is bamboo reinforced concrete, BRC, where we use the traditional concrete and we use the bamboo splints of particular sizes for as partial replacement or full replacement of reinforcement. In the other hand, there may be some of the structures where the structural members may be replaced by individual bamboos in single number or multiple numbers. So, talking about the construction using bamboo, both will be considered and our study will be related to both of them. Two studies will be related to the kind of structures where we use the individual bamboos, and another study will be related to BRC, bamboo reinforced concrete. So as visible, the left one figure is BRC, bamboo reinforced concrete. The lower second one is one footing kind of structure where the bamboo as a whole has been used. The lower right corner, it is a bamboo reinforced slab, and the top one, it is a bamboo truss using the whole bamboo. Going for the first study, talking about the traditional houses, the houses represents the characteristics of people living, conditions of climate, materials available, and workmanship practiced in the area. And as it is visible from the map of Assam or Northeast region, it is very much covered with dense forest or the forest. So obviously the bamboo is very much available in whole Northeast region. In Assam itself, the only bamboo cover is more than 10,000 square kilometer. In Arunachal Pradesh, it is more than 15,000 square kilometer. So bamboo is very much available, and if we can provide some engineered kind of structure with bamboo, whether it is a BRC kind of structure or it is individual structural elements, it will be obviously a win-win situation. So going for the figure 2, talking about the traditional houses, this is the view of a traditional Assam type house. In those houses also, the bamboo or ikra is used, and in figure 3, it is the traditional changhar, which is very much common for the people, all tribal people, the Misings, the Deuris, many tribes from Arunachal, etc., etc. And our first study will be about the changhars. Obviously, the bamboo houses are very much lightweight and economical and sustainable also. Talking about the earthquake hazard, we are in the seismic zone 5, and we have seen some of the very devastating earthquakes as mentioned in 1897 and 1950. Also, we have very much frequent earthquakes, as we had on 14 September 5.5 scale earthquake. On February 22nd also we have a 5 scale earthquake kind of thing. But the point is this: we are very vulnerable while in this region, and for that purpose obviously we have to think of a proper solution. Now, when talking about the seismic response, we know that the base shear is dependent upon the seismic weight as well as the AH into, it is AH into W. VB base shear is equal to AH into W, and obviously the base shear is directly proportional to the seismic weight. So if we can somehow reduce the seismic weight, obviously the base shear will be reducing and the vulnerability will be reducing, and this is the plus point with all bamboo structures or the wooden structures, etc., etc. Now, why bamboo, not wood? Because bamboo is having some inherent facilities over wood. A full-fledged bamboo tree will be ready for the construction in 3 years, while wood or a tree will take 20 years for the full-fledged growth or to be ready for the construction. From that point, the bamboo is very much favorable because in 3 years, the bamboos can be used. The life cycle is shorter, so it is more favorable. Objective of study is to study traditional tribal houses, especially changhars of Northeast region, and analyze existing traditional tribal houses. And so for that purpose, we have to actually study the joint characteristics, how the traditional buildings are having the joints, because to get the response or to study, we have to analyze it in a software. So this study was done to know the properties of the joints, traditional joints. These are some of the literature reviews. The case study was done in the Namdeuri village, which is at a location of 17 kilometers away from our college. And there was survey for different kind of, this is a Deuri Gaon, Deuri village. So there are lot many changhars. So they went through some of the changhars and it was then classified into various categories. So looking through the figure, so bamboo floors in the changhars are uh, uh, typically of this kind. Is my cursor visible?
Yes, ma'am.
Okay, is my cursor, so actually there are beams. Actually there are beams. On the beams, there are whole bamboos. On the whole bamboo, there is another layer at 90 degree, which is the half bamboo, and on that only the basic the floor kind of bamboo material is laid. That means the load bearing characteristic was very well followed in the traditional buildings. It is kind of grillage foundation. The load is transmitted first to the smaller one, half bamboos, then to the whole, then to the wooden beams or big whole bamboos. So the general descriptions of the buildings surveyed was classified into different categories. Let us take 6 of them. House number 1 was CBZ. C means the concrete stills, B means the bamboo chang, and Z means the galvanized sheet. Likewise, house 2 was also the concrete stills, bamboo chang, and the galvanized sheet. Then house 4 was BBZ, means the bamboo stills, the bamboo chang, and the galvanized sheets. When with the proper photo, it will be more clear. CBZ, the columns were concrete columns. Then the bamboo chang, the floor was bamboo chang. There was only the concrete columns there. And the roof is galvanized iron sheets. The roof may be a bamboo roof truss or a wooden roof truss. Likewise, H3. H3 also CBZ. So it is a concrete stilt. And H4 is a bamboo stilt, bamboo frame, and all the components are made of bamboo. There are some other category also. For example, CRZ. For those, the steels are concrete, the floors are also reinforced, and the roofings are the galvanized iron. Now talking about H5 and H6, they are nothing but basic reinforced concrete structures because they are having reinforced, that means reinforced columns or steels, and reinforced beams and reinforced floors. Talking about H4, which is having a whole bamboo joints, we are going to talk about this kind of structures. H4 BBZ, that means bamboo stilt, the bamboo, obviously floor supported by bamboo beams, and then the galvanized iron sheets. This may be thatch sheet, no problem. That means the whole structure is made up of bamboo. The methodology was first to design the analyze the bamboo steel house in SEP 2000, and going for analyzing in SEP 2000, there came some problem because bamboo, as it is very much available, the bamboo joints are not like the RCC joints. It's very difficult to assign the property on the bamboo joints, and it's so the modeling is very much complicated. Anyway, assigning normally the model was done. The taking the model geometry as in case of H4. Bambusa tulda, the Zatiba bamboo species were considered, and the bamboo cross section was designed. The various parameters were taken from NBC 2016 part 6, and section designer was used to design the bamboo section. The other information was taken from part 6 NBC 2016. And the concrete steels were also modeled. They are having no problem because this is basically a RCC kind of structure. Now, assigning the basic joint properties was a difficulty, and so our problem, we tried to solve it by testing some models in a shake table. So RFRI, the Rainforest Research Institute, was requested, and they provided us these models. The speciality of these models is that normally what happens, because we have a very small shake table, so base of our structure has to be limited with a size of 30 centimeter by 15 centimeter. We cannot go beyond that because we have a very small shake table. So for that purpose, with different heights, 4 models were prepared. But taking the bamboo for the model, there was some problem. Because the model was small, we have to take the topmost part of the bamboo. But as a natural material, the bamboo has different thickness. The thickness of the bamboo gum is very high in the lower portion, and it becomes smaller in the higher portion. So if we take a smaller cross section, it is not going to replicate the actual situation. So it was the problem. RFRI solved as the problem. They use the Noga Bijuli Ba. The Noga Bijuli Ba is smaller in diameter, and they are having the same characteristics. These small bamboos are actually the full-fledged bamboos, and they are maintaining the geometry of our Voluka Ba or Zati Ba, Voluka bamboo or Zati bamboo. That means in the small diameter also they are maintaining the inner diameter by outer diameter ratio. So these 4 models were used for our purpose. So this horizontal shake table was used for the testing. At the first, the shake table was validated with a steel model because it was already tested, and its natural frequency was found to be 6.4 hertz. And while tested, it was giving 6.4 hertz, so it was validated, and experiment was already done, and it was matching with a published literature. And then when both the results tallied, we can go for now for the testing of our bamboo models. The analysis was done in Campana software. That means the recordings were done in Campana software. The accelerometers were attached, and this is the arrangement of the shake table. The 4 models were arranged there. There is a plot of displacement, velocity, and acceleration in Campana software. The readings were taken, and this is all about the models. In the front view and side view, Noga Bijuli Ba, the average diameter was 0.3 meter and thickness is 0.005 meter. So this is the close view of the various joints which were used and which was approximately similar to the real life joints. And in the figure 35, it is a real life joint in a bamboo changhar, and our model replicates the same kind of joints. So, but one problem is there, as our model is very small one, we cannot model a interior joint. It is all about 4-column model, so we can only model an exterior joint. Anyway, the testing was done. So these are the sum of the results. This is the response of 0.9 meter frame on shake table. 0.9 meter frame was the highest frame, and this was the top displacement, 15.004. The lower line is the base displacement. The upper line is the top displacement. In the x-axis, it is the frequency. In the y-axis, it is the displacement. And we got this value, and we got the maximum displacement corresponding to the given frequency over here. So 6.45 hertz was, as we see that there was resonance kind of thing, we can determine that the natural frequency of this particular frame is around 6.45 hertz. So it's, if in radian, it is 40.52 radian for the highest model. Similarly, for the other models also, the recordings were done, and we got this kind of values. These are corresponding to model 3, model 2, and model 4. After doing the analysis in Campana software, the hand calculation was done. This is a very small problem. K can be found out with calculating the I, and Young's modulus was taken from the literature, and these are the calculated natural frequency. These are the calculated natural frequency for the models, because we can find out K, we can find out EI, everything is there. So stiffness natural frequency of the bamboo frame models can be found out by the calculations. Then the natural frequency found in SAP and natural frequency found by the formula is somewhat different. Small difference, but there is difference. This is in SAP, this is natural frequency found by the formula. So this is about the mode shapes of the frames. So then what was done actually, while using the formula, it was considered the moment to be fixed moment, then the moment was released, and then one process was done, iteration was done for bamboo framed model. In the SAP model, the moment was partially released to match with the natural frequency. The natural frequency originally obtained was 108.28. As we go on releasing partially the moments, obviously it was nothing but an iteration process, and in the iteration process it was trial and error kind of thing. And as we know, if it is a bamboo structure, it is not like kind of gluing, or it is not like a reinforced concrete structure. It is not a fixed joint. It is not a hinge joint. It is not a pin joint. The properties are different. So this was a trial and error method to get the approx situation of the joint of a bamboo structure. So traditional joints are flexible in nature. That means the bamboo joints are flexible in nature. So they partially allow the members to rotate. So this is the reason that we partially release the moments, and after doing the iteration, the release of the moment 0.4 kilonewton meter per radian was giving the best result. So it's a kind of this is a kind of process by which we try to make some arrangement so that we can analyze the bamboo structures in SEP, because there are, as defined, there are very minimum literature about the bamboo reinforced building or bamboo buildings. So this study was about to get a proper representation of the behavior of the joint by iterating the by iteration of partial release of the moment. So these are the results. The model with partial moment release is a real life representation of the bamboo changar, as the correlation was found out by experimentation of 100% bamboo models. And this is about the no release moment and with partial moment release. So time period will be obviously high, because if we release the moment, obviously with partial moment release, the time period is going to be high. This is the calculation for the time period. And this is all about the frequency. Obviously, for no release moment, the frequency will be more, because frequency is root of k by m. K is more, so there is more frequency, and with partial release, the moment in the structures will be lesser. And this is what is happening in bamboo structures. So this is our first study to replicate a total bamboo joint in a software, and for that purpose this particular work was done. Then comparison of the base shear with partial moment release, the base shear also reduced. If we consider it to be fixed, the base shear is high. With partial release, the base shears are lesser, and maximum joint displacement of the same model is more when the moment is partial release. And this is all about the study number 1. Now going to the study number 2, what happened? It was a model study, and in the model study, obviously there is some size effect, and in the model we could not actually replicate the inner joints, because inner joints are different in characteristics. So it was required that experimental evaluation, it was required that to get the total deflection data or to get the total rotational stiffness, we have to go for a prototype kind of thing. So the next attempt was to do the same kind of thing to get the actual representation in a prototype. In bamboo structures, normally 2 joints are there. In the outer side, these kind of joints are there so that the bamboo, along the cut part, the bamboo is placed. It is called the one-ear cut. And in the interior joints, the cut is U type of cut, which is a fish mouth joint. So these are the basic cuts in a traditional bamboo house. So a real-time bamboo frame was set out near the canteen of our college. So frame has been set up. The height was 2.2 meter and span is 2 meter. The ground was dug to provide the fixity or foundation. This was a frame which is replicating the joint of a real life changghar. So two joints were primarily adopted. Our testing was for one ear cut joint and the other was for fish mouth cut joint. The diameter of the column and the frame is averaging 90 millimeter. So figure 56, in figure 56, it is resembling the figure 53, the fish mouth, and in figure 57, it is the one ear cut joint. It is the outer side, and figure 56, it is the interior side. So National Building Code Part 6, Section 3 is providing some of the provisions for the joints. Lap joint, butt joint, bearing joint, etc., etc. The traditional bamboo joints, which has been used for years or decades, are generally of two types, and they are quite resembling to the bearing joints. The point is that it is just following, or it is in conformity, partial conformity with our suggested joints, but we don't know exactly about the joint behavior because in the softwares, no detailing about these joints are given. So there are some compressive strength tests for the bamboo parts, and these are compressive strength tests with the parts with nodes. The previous one was without nodes. Then fractural test was done. These tests were done for our given sample, but nowadays these tests are available in code IS 15912 2018. A bamboo code on construction is there, 15912, and many of the bamboo properties can be found out from that particular code also. But anyway, we need more literature. That particular literature is not sufficient for going for some kind of engineered bamboo structures. Then the laboratory test for tensile strength was also there. So tensile strength, then modulus of elasticity was found from the graph plotted. Some tests were done on the moisture content, and average moisture content of the samples when brought from RFRI was found to be 70.24. Then coming for the field test, fish mouth cut is like that, one ear cut is like that. The load versus rotation plot was done. It was difficult to load, so they loaded it actually with number of cubes because it gives in multiples of approximately 10 kgs against the load. They found out the rotation, and finally the rotational stiffness for the fish mouth joint was 4753 Newton meter per degree, and one ear joint was 3894 Newton meter per degree. And it was found that the rotational stiffness in the fish mouth joint is more than one ear joint, and this is the calculation done from the graph obtained from load versus rotation graph. And this was moment versus rotation graph. This is the moment versus rotation graph. some trend line was obtained, and those rotational stiffness values are the real life rotational stiffness values which can be used for a modeling purpose. Then modeling of the frame geometry in ANSYS software was done. The two different joints was simulated in ANSYS as a bearing provided with a revolute joint and a rotational stiffness. The experimental deformation was 9.7 millimeter for fish mouth joint, and ANSYS deformation gave 10.93 in the fish mouth joint, and for 1 year joint it is 12.5 and 12.656. The deflection on both the frames is calculated at exact same loading of 2960 Newton for better comparison. Since the difference in changes is not by much extent, this validates the physical and mechanical properties of bamboo. Because the final deformation was considered at 1960 Newton, the physical load, so these comparisons has been done on 2960 corresponding to 2960 Newton. So the deflection comparison was done for the experimental frame and the ANSYS model. For the experimental frame, it was slightly lesser. For the ANSYS deformation, it is slightly more. So maximum joint displacement was also placed, and maximum joint displacement was compared with this study to the previous study. The previous study with the bamboo models in SEC table, and there was 5.55% difference and 15.54% difference in the joint displacements in both the cases. These are the mode shapes of the bamboo structure for model analysis. And from these two studies carried out, some kind of insight was obtained regarding the joint characteristics of the real bamboo frames which are traditionally used, and this is going to help in analyzing the traditional changhars where all bamboo joints has been used, or bamboo or wood joints has been used, because for concrete kind of joint there is no problem. The problem is only there when bamboo and bamboo or bamboo and wood is there, because there the tying material is either the ropes or the wires or some kind of this kind of material. So these two studies were related to bamboo structures where the bamboo in individual or bamboo in multiple cases are used. The second study is about bamboo reinforced concrete. The bamboo species for the project was obtained also from RFRI, Rainforest Research Institute, Jorhat. And RFRI Jorhat is now housing about 43 species under 3 generic heads. We took out of them the most common 4 species, the Bholuka, Zati, Kako, and Mukalba, for our study. This is actually the continuation of another study. For the time constraint, I'll be discussing this study and I'll be briefly explaining about the previous study. This is the Bambusa balqua, holuka ba. This is the Bambusa tulda, jati ba. This is the Bambusa newtons, mukal ba. And this is Hamiltoni, this is the kakoba. Properties of different bamboo species are given over here. The density, modulus of rupture, modulus of elasticity, and maximum compression can be found out, or they can be taken from the literature. And they were also taken from the literature. For the previous experiment, for the previous study, we did it in our laboratory, but for this purpose, we have taken it from the literature. Now, here we are going to construct beams, bamboo reinforced beams. So for that purpose, there are actually two basic problems, and along with there is a problem of decay. The problem number one is moisture-induced dimensional instability. This moisture-induced dimensional instability we are going to address after some time. And the other one is pore interfacial bonding. This also we are going to address after some time. But the basic thing is that the bamboo is very much prone for decay by insect attacks, fungi attacks, etc., etc. For that purpose, CCB treatment is done, and the other traditional methods are there, but for the bamboo splints, CCB treatment or CCA treatment is considered to be better. And RFRI actually provided us with CCB treated bamboo splints. For our study, 24 bamboo reinforced concrete beams were cast with 16 mm and 20 mm dia bars as reinforcement. It was a total replacement of the steel bars. Previously, we did some of the study with partial replacement. For example, 2 bars with bamboo and 2 bars with reinforcement. This study we have done with total replacement, and beam size was 15 centimeter by 15 centimeter by 70 centimeter. The purpose of taking this size was to enable it to put in the flexural testing machine. M20 grade concrete was used with 0.45 water cement ratio, and OPC cement was used. The sand was zone to sand. The basic process for preparing bamboo reinforced beam was first the selection of bamboo, then cutting bamboo in size of 70 centimeter, which was done in RFRI, then splitting it into a proper size of 16 millimeter and 20 millimeter to replicate the real life steel reinforcements. Then CCB treatment was done, and these are the bamboo splints provided from RFRI with CCB treatment. Then comes the moisture-induced dimensional instability. For moisture-induced dimensional instability, the problem appears the swelling and shrinkage of bamboo reinforcement is a serious limitation. This is the problem. First, within the concrete, the bamboo will be like that. Then, soaking the moisture from the concrete, the bamboo may expand, and while contracting, it is reducing in the size, just creating some gap, finally reducing the bond. In both the cases, it may split the concrete or there may be lesser bonding. To address this problem, the epoxy is applied. The epoxy coating on each of the bamboo splints were done. Then the other one is the pore interfacial bonding. For poor interfacial bonding, the bamboo was rolled with GI wire. There was another study. The bamboo splints, which were epoxy coated, were actually rolled by different kind of wires, by ZI wires, then by coir and other threads also. And there was a test and pull out. There were pull out tests, and finally it was found that epoxy coating with ZI wire gives the best bonding. We have a paper with Abhijit Day, Elsevier paper, in that the frictional properties has been carried out and the best frictional properties were exhibited by rolling with GI wire. Now the splints are ready. That means our new reinforcement are ready. Then casing with the steel stirrups and preparation of the concrete was done. Beams were cast, vibrated, cured, and tested. The beams were tested in two forms, one in flexural testing machine and other one, in both cases flexural testing machine, this is a static one, the other one in UTM. Here we are taking into consideration of 4-point loading case. 4-point loading means the supports are there. We have 70 centimeter long beam, the two loads, that means the two cross beams are over there and load has been applied over there. The purpose of using the 4-point loading and not using the 3-point loading, that means we could have put one load at the mid also, is that in case of 4-point loading, you see this is the shear force diagram. For shear force diagram, this is the left shear force diagram. The middle portion, in the middle portion, there is no shear force. In the last 1/3 portion, this is with shear force. So the mid portion is free of shear force. And so that's why for that purpose, this portion is free of shear force and we can get the condition of pure bending. And that's why the 4-point loading case has been adopted. So tests were done in our regular flexural testing machine as well as in UTM. And the results were just like that. The beams were tested for 28 days, 45 days and 60 days. This is normally in the flexural testing machine. And load, maximum load they carried was for Bholuka Bah, it was 89.89. For Zatiba, it is 95.79. For Mokalba, it is 92.383. And for Kako, it was 71.46. This is in the flexural testing machine. So this is about, the previous one is about the 16 millimeter splint. These results are about the 20 millimeter splints, bamboo reinforced beams. These are the results. Here the results are slightly in the higher end, as the reinforcement, bamboo reinforcement is more in the diameter. The area of, not steel, the area of bamboo is more area of the, so that's why it is more in nature. So this is all about the results of flexural testing. Then comes the results under universal testing machine. The load extension or load displacement was carried out Load displacement curve 16 millimeter splint was carried out. Then load displacement, this is corresponding to 45 days and 60 days. And it was observed that the Jati Bah is represented by indigo, Mokal Bah is by green, Bholuka Bah is by mehendi, and Kako Bah is by red. In most of the cases, Jati Bah showed the maximum values, and Jati Bah and Bholuka Bah was better in the performance, and the worst performance was by Kako Bah. Here also load was found, the maximum load that can be taken by the beam was found. This is load displacement curve for 20 millimeter splint. Also here, this is corresponding to Jati, this is corresponding to Bholuka, this is corresponding to Kako Bah, this is corresponding to the Mokal Bah, and these are the load displacement characteristics. And this study for the beams can be extended for longer lengths, because for the easiness of the calculation and we have the limitation of testing the flexural behavior. The length is limited to 70 centimeter. That's why we could go for this kind of short beams also. So there may be some kind of simulation to get the proper behavior of bamboo reinforced beams for the longer lengths, and this study can be then used for the design purpose of some bamboo reinforced structures and behavior of beams. Now, till now, there is not any kind of literature or any kind of code other than 15912 where the behavior of the bamboo reinforced flexural members has been done. So this is a very emerging field, and this particular study can be carried out to get a proper insight of the behavior of the bamboo reinforced members, bamboo reinforced flexural members with different grades of traditional concrete. So this is all about. So my special thanks goes to Saurav Juti Datta, who was my master student, did the first part of the study, that means the 4 frames. Then Hussein Mohammed, who did the prototype study. Dr. Ovizit Day, I did not properly explain his part. He was working with the frictional properties of bamboo with different kind of tying material, and his result was used by Mukunda Madhav Bora for the last part of my presentation. So thank you all.
Okay, madam.
Thank you, ma'am. I request the participants to ask questions by yourself by turning on your audio. If you have any questions for madam. We can also take a few questions in the chat box.
Yeah, or if any document or any data or any information is required, you can contact me also. My contact number and everything is available in my college website. There are some other studies on bamboo bamboo frames and bamboo reinforced concretes. Also, some other students has done. If someone is interested, they can contact me.
Ma'am, there is a question in the chat box. I can read that for you.
Yeah.
It is from Pratima, a participant here. How to check attainment of sustainability in case of use of bamboo in RCC?
Please repeat the question.
How to check attainment of sustainability in case of use of bamboo in RCC?
Yeah, sustainability has different parameters. If you talk about the carbon footprint or this kind of things, obviously bamboo is in a bigger hierarchy, because for the construction of steel there are so many pollutions are going to be happen. So obviously we are going to get, or we are going to attain a better sustainability with bamboo structures. But one thing is there, to get a very standardized engineered house, because there is no statistics related to bamboo structures. Just like we have the characteristic strength of concrete or some equation, these kind of things are yet not coming from bamboo reinforced concrete or bamboo structures. So as I am from structures, there is some problem in suggesting some kind of design. Anyway, some of the small buildings are coming for us, which we go for vetting. But regarding sustainability, obviously the bamboo is in a greater hierarchy because less carbon footprint. It's only coming from the forest, and the cost related, the raw material cost is very less. But for preparing it, just like we are providing, we are making the splints, then putting in the CCB treatment, then you are rolling with GI wires, then applying this one epoxy and all these things. This makes it costly a bit, but still it is less than 50% of the cost of the steel. Once we did a calculation, it was about 35 to 40% of that of cost of the steel, because the labors are costly. For applying epoxy and all these things, the labors becomes costly, and that's why the bamboo splints are becoming costly. Otherwise, it is sustainable from the environment point of view. It is pocket friendly and very good for kind of low cost housing, disaster resilient structures, and it is very good for rural construction initiatives.
Thank you, ma'am. We have another question here.
Yes.
Which type of joints is more better between fish mouth and ear cut? As you have mentioned that fish mouth cut has more rotational stiffness than ear cut.
Actually, it's dependent upon the location also. Your fish mouth is comfortable when it is in the inner panels, because it is U type, no? So when it is inside, that means it is in continuation, fish mouth is the best one. When towards the end, the ear cut, one ear cut is better, because it is providing constraint. One part is left, and this is providing constraint from slipping or rolling of the bamboo towards the outside. So it's actually, it's not about the rotational stiffness only, it's about the location, because it was the traditional practice, and many a times the traditional practice are good, as it is now in the code which was published in 2018. The code, the bearing joints are given, and surprisingly these bearing joints are just like those joints which has been used by decades or years by the tribal people. So this is this is dependent upon the location also.
Ma'am, we have more questions here.
Yeah.
another one from Pratima, that is there any methodology or software to get the results of life cost analysis?
For life cost analysis, I have not used any software till now.
So
But
another. Mhm.
but people from construction management, they might have some software. From construction management field, I am some structures field. Obviously, there will be some kind of calculation for life cost analysis, because
Okay.
they are doing for some other kind of structure, other kind of, not for bamboo. Some project is going on by some of our colleagues for life cost analysis kind of thing. So they are from construction management field. Obviously, there will be some. Yes.
Thank you, ma'am. We have question from Dr. Snehal Kaushik, that
Yes.
how much strength difference in comparison with steel reinforcement of bamboo reinforcement in RC member? Have you done comparison?
Yes, for moment resisting, the kind of thing, in a previous study, it was 35 to 40%. But it was done, the kind of, it was done in the flexural testing machine in a previous study. This was 12 millimeter dia bars in a 15 by 15 beam and 12 millimeter splint. It was not more than 40% anyway, the flexural strength.
Okay, thank you, ma'am. Another question by Kishan. How does the anisotropy of bamboo affect its performance as reinforcement in concrete?
Actually, sir, it affects many ways. It's very difficult. The anisotropy, first of all, it is suggested that the bamboo, uh, wh- which are more than 3 years old, can be only used, and there are some specifications for using of the bamboo, not very lower portion, not very upper portion, the mid portion only. Then obviously the moisture kind of thing, the treatment kind of thing, then epoxy kind of thing. So, and again, from species to species, the strengths differ, and for the same bamboo itself, from point to point, it differs. So it is difficult, and because it is a natural thing, I myself has tested very fresh bamboo splints, very fresh members, which I have got a strength of approximately 210 Newton per millimeter square when it is coming from RFRI just treated. So after 3 months, it even do not give a strength of half of that. So there are problems, but RFRI people are doing also some of the studies in their own, but not on concrete the other way. They say that when it is within, when it is in the interior, that the strength reduction is lesser as it is as compared to when it is exposed. So anisotropy affects a lot, and this is one of the problems with bamboo because it is a natural material.
I hope the questions have been answered to the participants, and those were the questions that I received in the chat box, that we received in the chat box, ma'am.
Okay.
And then that calls for the end of the session. Thank you so much. There are also participants who have thanked you in the chat box.
Thank you so much.
Thank you so
Ma'am, I also would like to thank you for your informative session. It was wonderful to listen you, to hear you after so long.
Thank you all. Okay.
And
Thank
can
you,
we
ma'am.
have, Jay, can we have a group photo?
Yeah.
Yes, I would request everyone to turn on their camera so that we can get a picture. Okay, screenshot has been taken. Thank you so much, everyone.
Thank you, Jay. Thank you, everyone.
Thank you.
So with this, we come
Thank
to
you,
the
Jay.
end of today's
Thank you,
technical
everyone.
sessions.
Thank you.
Thank you all again. Good night.
Thank you,
Thank
Malcolm.
you. Thank you.